Today we're going to be doing notes on comparing proportions. This is chapter 22 in your textbook. Let's look for at the sample and distribution for p that we've been looking at. The expected value of p hat is p. The standard deviation of p hat is the square root of p q all divided by n. Now we're going to look at the sample and distribution for comparing two proportions. P1 minus P2 hat. The expected value of P1 hat minus P2 hat is P1 minus P2. The standard deviation of P1 hat minus PQ hat is the square root of P1 times Q1 all divided by N1 plus P2 times Q2 all divided by N2. Our null hypothesis being the null hypothesis equals P1 minus P2, which equals 0, implies that P1 equals P2, which equals some common value of P. How do we find this value? We take a weighted average of our two sample proportions. We'll call this P hat. On your formula sheet, it's shown as P. So this P hat would be x1 plus x2 all divided by n1 plus n2, which is equal to the number of successes in both samples all over the total number in both samples. Your calculator output uses p hat. So just remember that our calculator output would be p hat instead of p, okay? So we're going to go through and list what you need to do for your hypothesis test. You already know this, but there's a couple of different things when we're comparing two proportions, when there's a difference between proportions. So the name of this test is a two-sample test for the difference in proportions. Our hypotheses, our null hypothesis, would be P1 minus P2 equals 0. No difference in the population proportions. Our alternative hypothesis would be P1 minus P2 is greater than 0, or our alternative hypothesis could be P1 minus P2 is less than 0, or our alternative hypothesis could be P1 minus P2 doesn't equal 0. Now we need to check our conditions. Conditions must be checked for the hypothesis test and the confidence intervals. Okay, so they have to be checked for both. So 1, 2 independent simple random samples. There can be no link between the two samples, okay? Or individuals randomly assigned to treatments. Number 2, each sample is less than 10% of its own population. And 3, a large sample size. So to find that, you will have to take n1 times p hat 1 has to be greater than or equal to 10. n2 times p hat 2 has to be greater than or equal to 10. n1 times q hat 1 has to be greater than or equal to 10. And n2 times q hat 2 has to be greater than or equal to 10. Our test statistic, z, is p hat 1 minus p hat 2 minus p1 minus p2 all over the square root of pq times the square root of 1 over n1 plus 1 over n2. Where p hat is x1 plus x2 all over n1 plus n2. And remember, here on your formula sheet, they use p and q, but this would be p hat and q hat. And for our confidence interval, it will be p hat 1 minus p hat 2 plus or minus z star times the square root of p hat 1 q hat 1 all over n1 plus p hat 2 q hat 2 all over n2. You do not use p for the confidence intervals since you are not assuming p1 equals p2, which equals p. Let's look at our first example. The sickle cell trait is a hereditary condition that is common among Blacks and can cause medical problems. Some biologists suggest that sickle cell trait protects against malaria. That would explain why this found in people who originally came from Africa, where malaria is common. A study of Africa tested 543 children for the sickle cell trait and also for malaria. In all, 136 of the children had the sickle cell trait, and 36 of these had heavy malaria infections. The other 407 children lacked the sickle cell trait, and 152 of them had heavy malaria infections. 1, is there good evidence to suggest that the proportion of heavy malaria infections is lower among children with the sickle cell trait? And 2, give a 90% confidence interval for the difference in proportions with heavy malaria infections between those with sickle cell trait and those without the trait. First, we have to name the test. So this is a 2-sample test for difference in proportions. Then we need to define our difference in proportions. So P1 minus P2 equals the difference in proportions of African children with malaria. Sickle cell minus no sickle cell. Our null hypothesis is P1 minus P2 equals 0. Our alternative hypothesis is P1 minus P2 is less than 0. Our evidence for our alternative hypothesis would be P hat 1 minus P hat 2, which equals negative 0.109, which is less than 0. So now we need to check our conditions. So we were not told samples random. We'll have to assume they are. There's no reason to believe sample not independently chosen. So now we need to find N1 times P hat 1, which equals 36, which is greater than 10. N1 times Q hat 1, which equals 100, which is greater than 10. N2 times P hat 2, which equals 152, which is greater than 10. And N2 times Q hat 2, which equals 255, which is greater than 10. Also, 136 is less than 10% of African children with sickle cell. And 407 is less than 10% of African children with no sickle cell. So let's go ahead and look at the mechanics. Since they did not give us a significance level, we're going to set our alpha at 0.05. Our z is P hat 1 minus P hat 2 minus P1 minus P2 all over the square root of PQ times the square root of 1 over n1 plus 1 over n2. This equals 0.265 minus 0.374 minus 0 all over the square root of 0.346 times 0.654 times the square root of 1 over 136 plus 1 over 407. And then you would get negative 2.31. And you can go in and put all this information in your calculator like we did with a one proportion z-test. Here you would use a two sample test for a difference in proportions. And if you have questions on that, you can ask me in class because you need to use that to get your p-value. So our p-value is 0.0105. So our p-value is less than alpha because 0.0105 is less than 0.05. So we reject the null hypothesis. There's convincing evidence to support belief that proportion of African children with malaria is lower among sickle cell children. Okay, so one thing with this hypothesis test, this is not required for this one, but it might show up on your free response questions on your AP exam. So I just want to go over interpreting the p-value here. So this is how you interpret your p-value. So you would say the probability of getting a result as extreme as mine or more extreme given the assumption there is no difference in proportion with malaria, which is your null hypothesis, is very small. This is strong evidence against the null hypothesis. So now we're going to find a 90% confidence interval. So we need to name our confidence interval. So this is a 90% confidence interval to estimate P1 minus P2 equals the difference in proportion of African children with malaria and that is sickle cell minus no sickle cell. Our conditions were already checked in the hypothesis test. So if they haven't been checked and you're only finding a confidence interval, you'd have to check them here. And now our confidence interval is P hat 1 minus P hat 2 plus or minus Z star times the square root of P hat 1 Q hat 1 all over N1 plus P hat 2 Q hat 2 all over N2. This would be 0.265 minus 0.375 plus or minus 1.645 times the square root of 0.265 times 0.735 all over 136 plus 0.374 times 0.626 all over 407. Our confidence interval ends up being negative 0.182 to negative 0.035. I am 90% confident that the proportion of malaria cases among African children with sickle cell is lower than among African children without sickle cell. By 3.5% to 18.2%. Notice that 0 is not in my confidence interval. This means 0 is not a plausible value. For the difference in these proportions. There appears to be a difference in these proportions. This is consistent with my hypothesis test results.